A full 360-degree rotation. You return to your starting point. This is one of the most fundamental, unshakable truths of our physical experience. It's the axiom upon which geometry, engineering, and our entire spatial intuition are built. A clock hand returns to its position. A planet completes its orbit. A dancer finishes a pirouette. Yet, at the most fundamental level of reality, the level of the particles that construct you, me, and the entire cosmos, this axiom is a profound and spectacular lie. For the building blocks of matter, a single 360-degree turn is not a full circle. It is an act of transformation, a journey that leaves the particle fundamentally altered, a stranger to its former self. This isn't a metaphor or a philosophical riddle. It's a hard, experimental fact that shatters our classical view of the universe. The textbook definition of a full rotation is, for the quantum world, only half the story. To understand this cosmic deception, we must journey into the bizarre heart of quantum mechanics and confront a property known as spin. In the 1920s, physicists Otto Stern and Walther Gerlach conducted a landmark experiment. They fired a beam of silver atoms through an inhomogeneous magnetic field, expecting the beam to smear out on a detector screen. Classical physics predicted that the tiny magnetic moments of the atoms, like microscopic compass needles, would be randomly oriented and thus deflected by varying amounts. But that's not what they saw. Instead, the beam split cleanly into two distinct spots. It was as if the atom's internal magnets could only point in two opposite directions, up or down. There was no in-between. This was the first glimpse of a purely quantum property, one with no classical analog. They had discovered a particle like an electron or a proton possesses an intrinsic property called spin. The name is misleading. A quantum particle is not a tiny spinning ball. It is a point-like excitation in a quantum field. Its spin is a fundamental, built-in quantity of angular momentum, as intrinsic as its mass or charge. It doesn't spin, it's spin. This property is quantized, meaning it comes in discrete packets. Particles like photons, which carry the electromagnetic force, have an integer spin. But the particles of matter, electrons, protons, neutrons, quarks, all belong to a different family. They are fermions, and they possess a half-integer spin, most commonly spin 1/2. This seemingly small numerical difference is the source of the 720-degree paradox, and, as it turns out, the reason matter itself is stable. To grasp why, we must look at how physicists describe a quantum particle, not with a position and velocity, but with a wave function. This is a mathematical object, a cloud of probability that contains all the information about the particle. It has both an amplitude and a phase. The phase is often visualized as the angle of a clock hand rotating in the complex plane. While the absolute phase is unobservable, the end phase between two states is crucial. It governs how quantum waves interact with each other, creating the patterns of reality. Here is where our intuition fails. When you take a spin 1/2 particle, like an electron, and rotate it physically by 360 degrees, its wave function does not return to its original state. Mathematically and physically, its wave function picks up a negative sign, a phase shift of 180 degrees. It has been multiplied by -1. Think of that clock hand. Instead of returning to the 12 o'clock position, it's now pointing at 6 o'clock. The particle is in a state that is anti-aligned with its starting point. It's the same particle in the same location with the same probabilities of being measured, but its internal quantum state has been inverted. It is, in a very real sense, the negative of what it was before. To us, in our macroscopic world, this seems impossible. We can't perceive this sign change directly. But in the quantum realm, where interference is everything, this sign change is a matter of physical life and death. If this rotated particle were to meet an unrotated version of itself, they would interfere destructively, canceling each other out where they once would have reinforced each other. A full 360-degree turn has turned a particle into its own quantum opposite. It has been fundamentally changed by the act of returning to where it began. This forces us to ask an unnerving question. If the very definition of a full circle is contingent on the object being rotated, what does that imply about the geometry of space-time itself? Is our three-dimensional intuition merely a shadow of a deeper, stranger rotational reality? From that paradox, that dizzying revelation that a 360-degree turn is an act of inversion, emerges a profound answer. The universe does not operate on the simple geometry of vectors we learn in school, where an arrow returns to its starting orientation after one full rotation. The quantum realm, the bedrock of reality, is built upon a different, more elegant, and far stranger mathematical language. The entities that perfectly describe this 720-degree symmetry are called spinors. A spinor is a type of geometric object that lives in a more abstract space than a simple vector. While a vector in our 3D world can be visualized as an arrow with a length and a direction, a spinor is more subtle. It encodes not just directional information, but also information about its relationship with the very fabric of the space it inhabits. And its defining characteristic, the property that makes it the perfect language for describing fermions like electrons, is its rotational symmetry. A spinor requires two full rotations, a complete 720 degrees, to return to its original state. This isn't just a convenient mathematical trick invented to patch a hole in a theory. The concept of spinors, developed by mathematicians like Élie Cartan in the early 20th century, was seized upon by the physicist Paul Dirac in 1928. He was trying to create an equation that would unite quantum mechanics with Einstein's special relativity. In doing so, he found that he needed to use these strange spinor objects to describe the electron. The resulting Dirac equation was a monumental success. Not only did it correctly describe the behavior of relativistic electrons and naturally incorporate their spin one-half nature, but it also made a stunning prediction: the existence of antimatter. The mathematics of spinors demanded a mirror image particle for the electron, one with the same mass but opposite charge, the positron, which was discovered just a few years later. The universe's hidden geometry had pointed the way to a whole new class of matter. The 720-degree rule wasn't a quirk. It was a core feature of a theory that had successfully predicted a fundamental component of the cosmos. For decades, this remained a beautiful but abstract mathematical truth. Then, in 1975, it was made stunningly, tangibly real. A team of physicists, including Helmut Rock, Anton Zeilinger, and Daniel Greenberger at the Leo Langevin Institute, along with Samuel Werner's group in the United States, devised a brilliant experiment. They used a technique called neutron interferometry. The setup is a marvel of precision. A single perfect crystal of silicon is carved to act as a beam splitter. A beam of slow-moving neutrons is fired at the crystal. According to quantum mechanics, each neutron, behaving as a wave, travels down two separate paths simultaneously. One path is left clear, while the other passes through a carefully controlled magnetic field. This magnetic field interacts with the neutron's spin, causing it to precess or rotate by a precise amount. Finally, the two paths are recombined by the crystal and the neutrons hit a detector. The result depends on the phase difference between the waves from the two paths. If they arrive in phase, they interfere constructively and a strong signal is detected. If they arrive out of phase, they interfere destructively, canceling each other out, and the signal vanishes. The experimenters meticulously tuned the magnetic field to induce a 360-degree rotation in the neutrons on one path. Classical intuition says this should do nothing. A 360-degree rotation brings you back to the start, so the two paths should be perfectly in phase. But that's not what happened. At exactly 360 degrees of rotation, the detector signal disappeared. The beams were interfering destructively. This was the smoking gun. The wave function of the rotated neutrons was exactly 180 degrees out of phase with the unrotated ones. It had acquired that negative sign. The experimenters continued to increase the magnetic field. As the rotation approached 720 degrees, the signal returned, reaching its maximum strength at the 2 full turn mark. They had directly observed the 720-degree symmetry of the quantum world. Spinors were not just abstract math, they were physical reality. This bizarre rule is the foundation of the Pauli exclusion principle, which states that no two fermions can occupy the same quantum state. This principle is why electrons stack into shells around an atom, creating the entire field of chemistry, and why matter is stable and doesn't collapse into a dense soup. The 720-degree deception is the very reason the universe has structure. It is the silent geometric law humming beneath the surface of everything we see, proving that to truly return home, sometimes you have to go around twice.